Have you ever wondered what problems you might encounter with ER models? In the world of database design, entity relationship, or ER models, play a pivotal role. They are the blueprint, the roadmap, if you will, that allow us to conceptualize the structure of a database. But as with any tool, ER models are not without their quirks. They might oversimplify complex data relationships, create ambiguity due to unclear definitions, or even struggle to accurately represent the cardinality of relationships between entities. And these are just a few of the challenges one might encounter. But don't be disheartened. ER models, despite their limitations, are an invaluable asset for any database designer. Understanding their potential issues only enables us to better navigate these challenges and create more effective database designs. So, are you ready to explore this fascinating world of ER models? Let's delve into the most common problems faced with ER models. Firstly, ER models can often oversimplify the real-world domain they're representing. Imagine trying to squeeze the entire universe into a tiny box. Sounds impossible, right? Well, that's a bit like what we're trying to do when we create an ER model. We're trying to capture all the intricacies and complexities of a real-world system in a format that's, well, decidedly less complex. So, what happens? Complex relationships, intricate business rules, or detailed data constraints might not be fully represented in the model. It's a bit like trying to paint a detailed landscape with just a few broad strokes. The result can be a model that gives an incomplete or even misleading view of the system. This could lead to misinterpretations or oversights when the database is built, leading to potential issues later on. So, oversimplification can lead to some serious complications down the line. Next, we have the problem of ambiguity. Now, ambiguity in ER models stems from unclear definitions of entities, attributes, or relationships. Imagine a situation where an entity is vaguely defined. This can lead to differing interpretations of the model among the various stakeholders, be they developers, project managers, or end users. For instance, let's consider the entity employee. Without a clear definition, one could interpret it as a full-time employee, while another might consider it to include part-time workers or even contractors. This ambiguity can cause a ripple effect, impacting the relationships and attributes connected to the ambiguous entity. Similarly, if an attribute or relationship isn't explicitly defined, it can lead to confusion. Does the salary attribute include bonuses and commission? Does the reports to relationship imply a direct or indirect reporting structure? These are not just rhetorical questions, they highlight potential areas of confusion that can arise from ambiguity in ER models. Thus, ambiguity can lead to misunderstandings and miscommunication. Another issue is the inadequate representation of relationship cardinality. As we delve deeper into the world of ER models, we stumble upon the problem of how they represent the cardinality of relationships. Cardinality, as you know, defines the numerical attributes of the relationship between two entities. It's a pivotal aspect of any database design, indicating whether we're dealing with one-to-one, one-to-many, or many-to-many relationships. However, ER models often fall short when it comes to accurately representing these relationships. This is particularly true for complex relationships that don't fit neatly into these categories. For instance, an ER model might simplify a many-to-many relationship as a one-to-many relationship, which can lead to misinterpretations. The oversimplification of these relationships can result in a flawed understanding of how entities are interconnected. This, in turn, can impact how we design and interact with our database. Inaccurate relationship cardinality can cause a flawed understanding of entity relationships. ER models also struggle with accurately representing many-to-many relationships. This challenge arises due to the intricate dynamics that many-to-many relationships present. Imagine two entities, students and courses. A student can register for multiple courses, and a course can have multiple students. This is a classic example of a many-to-many relationship. Now, to accurately represent this in an ER model, we introduce what's called an associative entity, or table. This new entity, let's call it registration, acts as a bridge, linking our original entities, students and courses. Each record in the registration table represents a unique combination of a student and a course, effectively breaking down the many-to-many relationship into two simpler, one-to-many relationships. But here's the catch. While this approach does solve the problem, it also adds an extra layer of complexity to the model. The addition of associative entities or tables can make ER models more intricate and thus more challenging to understand. So many-to-many relationships can make ER models more challenging to understand. Now, let's talk about how ER models struggle with complex business rules. In the world of business, rules and constraints can often be intricate and multifaceted. These complexities can become a real challenge when attempting to represent them in an ER model. Imagine a business rule that says a customer can only place an order if they have been a member for more than 6 months and have a credit rating above a certain threshold. This is a relatively complex rule involving multiple entities and conditions. Unfortunately, ER models might not be equipped to represent such intricacies effectively. As a result, these business rules often have to be implemented at the database level. This can involve the use of triggers, stored procedures, or other mechanisms. This approach, however, can lead to an increased level of complexity and potential for inconsistencies within the database itself. Therefore, complex business rules can pose a significant challenge for ER models. ER models also have limited support for representing hierarchical relationships. This issue surfaces most prominently when we're dealing with subtype and supertype relationships. Imagine you're designing a database for a university. You have entities like student and staff, but both can be further classified into undergraduate, postgraduate, teaching staff, and non-teaching staff. These are subtypes, while student and staff are supertypes. In traditional ER models, this hierarchical relationship can be difficult to represent. This could lead to potential misunderstandings or oversights, especially when different subtypes have their unique attributes. For instance, an undergraduate might have a year of study attribute, while a teaching staff might have a subject specialization attribute. Some variations of ER modeling, like enhanced entity relationship models, do provide mechanisms for representing these hierarchies, but they come with their own complexities. So lack of support for subtypes and supertypes can be a serious limitation of ER models. Representing data that changes over time can also be a struggle for ER models. This type of data, often referred to as temporal data, is particularly challenging to depict in the traditional ER framework. Why so? Well, imagine you have data that evolves, changes, and morphs over time. The challenge here is to keep track of these changes without losing any historical data. Traditional ER models, as nifty as they are, don't quite have the mechanisms to handle this efficiently. This limitation can lead to potential inaccuracies or even loss of valuable historical data. It's like trying to capture the flow of a river with a series of snapshots. You'll get a sense of the river at specific moments, but you'll miss the fluid, continuous nature of its movement. So, time-varying data can pose significant challenges for ER models. But by understanding these limitations, we can explore techniques and adaptations to better handle this dynamic data. Finally, ER models have limited support for more complex data validation rules or constraints. While they can represent basic data constraints such as primary key and foreign key constraints, they often falter when it comes to the more intricate rules that govern data validity. These might include multi-table constraints or constraints that involve complex calculations or business logic. The inability to represent these constraints within the model can lead to potential data integrity issues. It can also result in an over-reliance on the database management system to enforce these constraints, which is not always ideal. The challenge here is that these constraints are essential in ensuring the accuracy and consistency of the data within the database. Without them, we run the risk of violating the very rules that keep our data reliable and meaningful. So, limited support for data constraints can be a significant limitation of ER models. So, as we've seen, ER models, while incredibly useful, come with their own set of challenges. they can sometimes oversimplify complex real-world domains, leading to potential ambiguity and misunderstandings. The cardinality of relationships between entities may not always be accurately represented, and many-to-many relationships can add unnecessary complexity. ER models can also struggle to handle intricate business rules and may not adequately represent hierarchical relationships or time-varying data. Furthermore, they may lack support for more complex data validation rules or constraints, and scalability can become an issue with larger databases. However, acknowledging these limitations is the first step towards overcoming them. By understanding the potential issues associated with ER models, we can work to mitigate these problems. This involves creating more precise definitions, considering alternative modeling techniques, and implementing data rules and constraints at the database level when necessary. By being aware of these potential pitfalls, you can work towards mitigating these issues and creating more robust and efficient ER models.